What's going on, everyone? Welcome back to another episode of Crypto Catch Up with me, Benny. Now, in this video, we're going to be going through homomorphic encryption. Now, the name itself sounds extremely complicated. What is homomorphic? Well, all of that we're going to go through. But the reason why we're going through it is because it's becoming even more pertinent in today's society as we worry about data breaches and the privacy of our information when we're conversing online and through our everyday dealings. Now, fully homomorphic encryption is known as the Holy Grail of encryption, and that's what we want to get to the bottom of. So let's get into it. Alright, so for a moment we need to give you a use case just so we can set the scene. I'm going to put this first image up. So you are a client, you are using your mobile phone. Now this is right now, in today's day and age. The data that we have is encrypted while at rest and also while it's on the move, whether it be via HTTPS or TLS or SSL. But when it gets to the server, in this case, let's say it's to do a search on Google Search or to edit a document on Google Drive, it has to decrypt that on the server side to be able to form any function on it before it can send it back to the client for them to review the output. Of course, this leaves holes in our privacy because it is decrypted at the point in which it's being worked on. That means that the server can store information about us and do a range of other things which obviously we may not be privy to. So how do we solve that? Well, what about if there was a scenario where when the data was at rest, when it was on the move, and when it was being computed on, it was encrypted the whole way? So it allows you to sort, search, edit, and the actual server itself would not know what was input or was output, only that they know that they pass back a particular ciphertext with a particular function applied to that client that requested it. That sounds pretty cool, and it is, but it's extremely hard to achieve. And that's why, to date, fully homomorphic encryption has been very limited in its application. But I want everybody to understand the reason why we should be supporting this, and of course, be keen to see when we're going to get something that's practical to be able to use this into the future. So why do we need it? Well, like I talked about, is that the conventional encryption schemes such as public key cryptography can't work on encrypted data. The legacy schemes require you to share a key, like your private key, in crypto or blockchain based solutions. And even if it's not shared, some data is sent unnecessarily. So an example of that is research. So when you have large data sets for a company, and they may want cancer researchers to have 3 fields of information, but it's easier for them to just send the whole lot instead of obfuscating it, because when you obfuscate data and it becomes unintelligible, it's no good to anybody. So obviously that's a risk. But of course, if we could compute on that encrypted data and get that result back without exposing the individual identities of these people, then we have a hell of a solution. There's also significant privacy concerns as cloud providers such as Google or Amazon, they own the data when it's unencrypted. This is massive in blockchain space and in cryptocurrencies, where if you don't own your keys, you don't own your crypto. If you leave it on an exchange, the exchange in this case being a cloud provider, Google or Amazon, you don't have control of it anymore. And what that could actually mean though, is that well after you've left the service, they're still storing metadata or personally identifiable information about you. And if they are then susceptible to a security breach later on, and they are attacked, of course that information is going to go with it. And so it all comes down to trust. Who do you trust? Are you going to trust Google, Amazon, Facebook with the amount of data breaches that they have every year? Or would you prefer to have a fully encrypted version at rest, in transport, and while it's being computed on? I know what I'd like. So what is homomorphic? Well, homomorphic comes from the ancient Greeks. It means homos, same, and morphe, shape, literally meaning same shape. And we'll get into what that means now. Well, the word's been coined by a number of industries and areas, one of those being abstract algebra, where they use it as a map preserving, a map being a function, all the algebraic functions, the inputs and outputs within a particular range of addition and multiplication. Now, for those of you who aren't into math, that's all gobbledygook anyway. But this one's a little bit easier to understand. Its application to cryptography. It's a kind of encryption scheme which allows a third party, a cloud provider or service provider, to perform computable functions on encrypted data while preserving the function and format of that encrypted data. It's as simple as that. You send them encrypted data, they can perform whatever function you like, whether it be sort, search, min, max or otherwise, and they will give you that response back. Now, in theory, like that, it's very simple to understand, but of course, it's actually very complex. So what's the history and where does it come from? Well, in 1976, we were graced with public key cryptography from Diffie-Hellman. Then in 1978, came along RSA, which was from Ravesh, Shamir and Alderman, and it was the first feasible achievement of public key cryptography in the world, and it exists to today. Then very shortly after that, in 1982, came RAD, from obviously Ravesh and Alderman of the original RSA protocol. Now, they actually used the term privacy homomorphism within their paper, which was explaining where it could be used. Now, like I said, it was a byproduct of RSA. They've realized that they could perform certain functions and keep the same shape of that data while doing so. But it wasn't until near 30 years later, a gentleman by the name of Craig Gentry, in his seminal PhD thesis, proved and provided an actual fully homomorphic encryption scheme and a general framework on how to achieve such. Nearly 30 years to come up with how you can encrypt data while it's being computed on and get an intelligible response back. But it's important to realize it didn't just all happen overnight. So if we take a look down here, RSA came out in 78, then we've had a number of other schemes along the way till Gentry here in 09. But you have a partially homomorphic encryption, and then came somewhat homomorphic encryption, and then fully homomorphic encryption. So it's important to understand what these other ones are before we move on to the Holy Grail of encryption. So, let's have a look at partial homomorphic encryption. What it allows is one type of operation with an unlimited number of tries. So you can add ciphertext together, but you can't multiply. So it's only therefore useful for a particular applications whose algorithms include either the plus or addition or multiplication. And as you can see here on the screen, RSA here was the first, and then we've had many that have come afterwards showing what homomorphic operation that it can do. And as we're well aware of, you're the client, you have some plain text, you encrypt it with a public key, and this is the actual RSA encryption scheme. It turns it into gobbledygook. You can then decrypt it with a private key, and obviously you can then use that data again, whether that's for a transaction in a blockchain based solution or transferring it over the internet or otherwise. Then you have somewhat homomorphic encryption. Now, somewhat homomorphic encryption is exactly what fully homomorphic encryption is built off, because it has one additional property over the partial. And that additional property is the fact that it allows you to do multiplication and addition, which allows you essentially to build any Boolean circuit or any logic gate, which we'll get into very shortly. But the downside of it was it only allowed you to do it a limited number of times. So as you did addition or a multiplication, the size of the ciphertext actually grew in a significant way. So it limited the number of real life applications that it could be applied on, because the scenarios were, very basic in which it could be used for. And the reason for this was because after a certain threshold of multiplication or, addition operations, the actual decryption function failed to recover the the original ciphertext and turn it back into plain text. And we're going to talk about that a little bit more once we get to the fully homomorphic encryption. before we move on, I just want to talk a little bit about these homomorphic operations in that of Boolean circuits. So Boolean circuits are something very common, whether it be in electrical circuits or even in that of software engineering. And it's essentially about logic. How can we add two things together and what would be the outcome of that? Because we must remember, computer CPUs or central processing units actually use binary on-off states. We're not at quantum computing just yet, so you have ones and zeros. And so this is a way for it to obviously evaluate particular functions, like we've talked about, sorting, searching, min, max, things like that. And this is what they look like here. And below is a truth table which shows you what it could actually evaluate to if A or B is on or off, or both on, both off. What is that scenario? Here is actually a final logic calculator that I built in my first year of university. It actually had no specific purpose other than that the university lecturer wanted us to build it with 4 registers and 6 different things at the top with a clock that turned on and off. And of course, at the end of the day, we wanted to get a green light here and no error. So it's errored here because it hasn't been initialized, just so you know. I did pass the assignment, but it was actually only using the AND, the OR the XOR gate. So inside this multiplexer, inside this D-type latch, there are more AND OR scenarios where you're having to make up the logic to be able to obviously evaluate the function that was desired by the assignment. So it is actually pretty interesting stuff. You can actually build one of these yourself with a software called Logicism. It's very cheap. Sorry, I should say it's free. So get that if you want to give it a go and have a look at it. But it's time to get into the Holy Grail. So, like we've talked about, the goal of fully homomorphic encryption is to be able to do an arbitrary number of homomorphic operations plus multiplication with unlimited number of times. So this here is the evaluation of it. This is what we're looking for. So the client encrypts his message M, encrypt message. They then send it to obviously the server. So you have the second one here. The client sends the encrypted message to the store, which is here. S, server evaluates it. Then the individual here, C, can query it on a particular function. So like I've said, cert, sort, min, max, whatever you want, edit it. Then the server evaluates it homomorphically and it returns that encrypted function with the message inside. And then of course the outcome is that they can decrypt the encrypted function with that message inside, and you recover the actual plain text that was sent initially, or I should say ciphertext in this scenario. So Craig Gentry's actual work was based on that of ideal lattices, or lattice theory, which is common in that of graph theory. If you've seen it, that is what directed acyclic graphs like iota, bit lattice, they're using this ideal kind of lattice or lattice theory in general to be able to do something that is much more powerful than what a blockchain can actually achieve. What that is, I guess, is because in the structure of that lattice, when you traverse over the different vertices, so you have nodes and vertices, you come up with relationships you never would have found otherwise. And it's a very powerful concept in the way that we store and process data. So lattice problems can't actually be solved efficiently and therefore are considered secure in a manner, which is a portion of why Gentry used this for his homomorphic encryption scheme. What they actually do is take the cryptographic algorithm in this circumstance and they compare it against what's known as a hard math problem. And this whole process is all about generating a proof known as a security reduction, the difficulty in which it would be to crack that algorithm. And so we reduce it to the point of one known hard problem and say, this is as strong as it gets. If you solve this, then it's all over, kind of thing. And that's where they get the idea of, how secure these kind of ideas or algorithms actually are. So public key cryptography algorithms are actually based on math problems like the elliptic curve logarithm problem. So you see that in Bitcoin with ESEDA, which can actually be solved with a quantum computer using the Schnorr algorithm, unlike lattice problems which cannot. So it's considered post-quantum safe at the point in time. So that's pretty cool. So what's the process? because it's not as simple as it seems. You can't just send the data, do an unlimited number of operations without something happening. So what actually Gentry came up with was an ingenious way to solve the actual size of the ciphertext growing over time. Because the fact is here, addition, when they did A plus B, it actually doubled it, the actual size of the ciphertext. Multiplication squared it. So you can imagine if you're doing a huge number of binary operations or Boolean circuits, it is computationally not only very expensive, but the size of the data is actually huge as a part of it. And of course, every operation is increasing the noise, which lowers our chance to be able to decrypt it later on and get that intelligible information out of it, which we saw in the other schemes. So he came up with two techniques. The first was squashing, and then once it was squashed, it was able to be bootstrapped. So let's go through these. So essentially I've put in white just a quick one-liner, and then the rest is more information, but it's like an re-encrypting scheme to get a fresh ciphertext from a noisy one. So first we squash it. The homomorphic decryption removes the noise from it. A new homomorphic encryption introduces then a small amount of noise to the ciphertext. And essentially what it's doing is you have this encrypted thing, you then add another layer of encryption around it. Then what you do is you evaluate that, you remove the actual inner encryption where all that noise was, and then you're left with that outer encryption with that fresh ciphertext. Then you can obviously compute more and more and more until you reach the threshold again where it goes, the noise in this is getting a bit too much, we're going to need to bootstrap and squash again. This happens again. And of course, the outcome of which is the fact that we can do this unlimited number of operations because of these two ingenious methods of squashing it, the decryption algorithm, into a complexity that the actual homomorphic algorithm can compute on. Now, as a portion of that, of course, bootstrapping comes with major overheads, and therefore it limits practicality because it's very computationally expensive to be able to do that. And that's the limitation of fully homomorphic encryption right now, is the fact that when we're computing ciphertext or plaintext data on our computer, it takes nanoseconds. But some of these schemes in the early days were 100 trillion times slower on the ciphertext than it was on plaintext on the same thing. So obviously that is something that we just simply can't use in a practical application. Squashing, it ensures the polynomial degree of the circuit is reduced to what the scheme can handle. So polynomials are like your x squared. As a part of that squashing though, it does add an assumption to its provable security scheme of the SSSP. Now I won't go into that, but this is all about giving you information out there to go and research if you are interested in how freaking cool this stuff is. So, what are the different schemes out there? Well, like we've talked about, Gentry based it on the ideal lattice. There are over integers, there's learning with errors problems, and there's the NTRU-like, which are very efficient, that we've had obviously, much more recently. Then below that you have a couple of different schemes and their actual running time. So like I've talked about, you're talking about a public key size here quite large. The generation took 2.2 hours to encrypt 3 minutes, to decrypt 66 seconds. That just simply is not suitable for everyday applications. It is too long, and this might not even be a complex problem that we're trying to solve. With that though, another complex problem that we have is simply that this is very complicated math. And with that very complicated math, it's really hard to embed into like a software development kit or into a library for people like you and I to go and use to be able to perform some data operations and see what the outcome is. The most common down the bottom there is HELib and Seal. So Seal is by Microsoft. HELib is actually probably the most up-to-date one there. I checked it out I think 2 days ago, and there was an update on their GitHub very recently. So that's awesome that it's being kept up to date, as obviously we come up with better ways to go about solving this problem. So the limitations, like I said, complex mathematical algorithms make it hard to create functional development libraries and tools. It's impractical based on computational overheads and time at the point in time. And it's mainly theoretical. So there's 5, 10, 15 schemes out there, but none of them have been able actually to be implemented on any problem because it's all very purely theoretical. Right, let's get into some interesting stuff. So the use cases, well, what would you want to use something where you can ensure that your data is fully encrypted from go to woe? Well, one of the big ones at the moment is medical applications. So in Australia at the moment, we have a system called the My Health Record. And the My Health Record is allowing doctors and other individuals to perform some operation. It might be to, see if you have something or to see what the script was that you were provided. And this is the same all around the world. People are using medical applications to not only do research, but to share data around hospitals to make that process easier for you if you've moved or even if you're injured overseas. Well, it's a perfect use case for this because you encrypt that data to the point where it can still be computed on, searched by these organizations, but they don't know what the input or the output is, other than the fact that it is found true or they're given the specific information that they asked for. Another really interesting one is delegated computation. Now, of course, if we're going to send something off to be computed on, even if, let's say, it's movie rendering, and we don't want viruses or malicious, software embedded within that, we can actually trust then that whatever server we send it to, whether they're malicious or not, will not be able to do that because the data is actually encrypted. They perform their function, they send it back to us, and we have obviously the private key to decrypt that and be able to use it as intended. And of course, distributed ledger technology. A lot of people are looking at how they can use this ledger-based system, which is allowing, pseudonymous identities of transactions, etc., but also that with data. So we have not only logging of what's happened, but the function to be performed on data while it's maintaining privacy-preserving properties. In the real world, Fujitsu Labs was the first one to do it in 2013 for statistical calculations and biometric authentication information. ShareMind in Estonia has used it to analyze data from Ministry of Education and Finance. So there are a number of use cases. It's finding the practicality in it though, but obviously it comes down to that question, like I said earlier, trust. Who do you trust with that information? And if you had a scheme like this, would it allow you to trust it more? So what's some other approaches? Well, because we've been talking about the Holy Grail of encryption, being able to do applications and functions on encrypted data and no one knows what the hell's going on essentially, there's got to be another way because we haven't reached a practical time where that can be used in most applications. So some of the other options are this: secure multi-party computation, so MPC. It essentially breaks up servers and they're each given a portion of that unintelligible data. It encrypts those shares of data and you can have an unlimited number of shares. So for an attacker to compromise it, they would need to have, a certain number of servers to get the data. It's kind of like the 51% attack in Bitcoin or in blockchain-based systems. So the likelihood of failure of actually, obtaining that information or the data grows for a large number of servers. Therefore, it assumes some level of non-collusion is going on, because of course, if you owned all the servers, then they could possibly put the, data back together. We have zero-knowledge proofs, which came out in the 1980s. Everyone knows about these. These are awesome, and of course, ZK Snark, so succinct knowledge arguments. Zero-knowledge proofs are great for authentication, but they're not good for really anything else. They're a yes/no statement. It's a proof to you that I know the answer, of something, but nothing more than that. Then you have deterministic, order-preserving encryption, so OPE, but it only allows for some form of functions as well, which makes it just like some of the other schemes within the homomorphic encryption world. So where can you get more information? Well, I actually found that this book, Fully Homomorphic Encryption and Real-World Applications, is due to come out at some point in this year from Springer. So if you're into this, I highly recommend getting that book when it comes out. It most likely will be very expensive, but I'm sure it's going to be very interesting. If you have a mate at university, get them to download it for you. And down the bottom, I found a great article or a paper, I guess, called a survey on homomorphic encryption schemes. That was originally posted in 2016. It actually got approved to go into the Australian Computer Manual in 2018, I believe. So it's fairly new in that, and it's actually a really good breakdown of all that information. So that's a long video, but I hope you've got a really good understanding now of where homomorphic encryption has come from, the different kinds, or partial or somewhat, but then of course, what fully homomorphic encryption would mean for us in today's day and age with the privacy and data breaches that are going on. Essentially, the reason why it's a holy grail is because it will allow us to trust any party with our data and allow us to compute on that and do anything that we would do in our normal daily lives. Of course, we're still waiting for that to become practically available, with simply the ciphertext growing too greatly, too quickly, and making that math very complex. We have a long way to go still, even though it came out, obviously, in the early 1980s. So, that's all I have. If you have any questions, leave them below. I'll try and post some links and the resources and provide you the slide links as well. Enjoy the rest of your day.